Late August 1944, Marienburg Testing Grounds, East Prussia. American technical intelligence officers stood before 70 tons of German engineering ambition. Tiger No. 507, a Tiger II heavy tank, Germany's newest and most powerful armoured vehicle, captured intact during the Soviet summer offensive and somehow diverted through intelligence channels to American evaluation teams before being shipped to the Soviet Union. The tank represented everything German heavy tank design had become by the war's final year. Frontal armour 180 mm thick, an 88 mm KK-43L/71 gun capable of destroying any Allied tank at ranges exceeding 3,000 meters, combat weight of 69.8 metric tons. The heaviest operational tank to see significant service in World War II. But within 72 hours of beginning mobility trials, American engineers would document fuel consumption so catastrophic it defied rational military planning. 2 gallons per mile under combat conditions. An operational range of barely 60 miles with full fuel tanks. A logistics burden so massive that even Germany's sophisticated military supply system could not sustain Tiger II operations across extended campaigns. The Tiger II would prove to be not Germany's ultimate weapon, but rather the ultimate expression of a design philosophy that prioritized individual tactical superiority over strategic sustainability. A philosophy that would help lose Germany the war, despite creating the most powerful tank ever deployed in significant numbers during the Second World War. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Tiger II emerged from German response to Soviet heavy tank development and the approaching inevitability of fighting a defensive war on German soil. By early 1944, German intelligence had identified the Soviet IS-2 heavy tank mounting a 122 mm gun capable of defeating Tiger I frontal armor at combat ranges. The Wehrmacht Weapons Procurement Office demanded a new heavy tank design that would restore German armor superiority. Henschel und Sohn, the company that had developed the Tiger I, received the contract in January 1944. The design specifications called for frontal armor, sufficient to defeat the Soviet 122 mm gun at all practical combat range, a main gun capable of destroying any current or projected Allied tank beyond 3,000 meters, mechanical reliability superior to the Tiger I, which had suffered notorious transmission and final drive problems, and critically, fuel consumption comparable to or better than the Tiger I, which already consumed fuel at rates German logistics struggled to support. These requirements proved mutually incompatible available technology, but German engineers proceeded with development anyway under direct pressure from Adolf Hitler, who personally reviewed Tiger II designs and demanded maximum armor protection and firepower regardless of other considerations. The production Tiger II that rolled from Henschel factories beginning in January 1944 represented sophisticated engineering applied to increasingly desperate strategic circumstances. Combat weight of 69.8 metric tons placed it 13 tons heavier than the Tiger I and nearly 40 tons heavier than American Sherman medium tanks. This enormous weight resulted directly from armor protection that exceeded all previous tank designs. Frontal hull armor measured 150 mm thick, sloped at 40 degrees from vertical. This sloping increased effective thickness to approximately 185 mm against direct frontal hits. The principle, copied from Soviet 34 design, meant that even thick armor became more effective when angled to increase the distance a projectile must penetrate. Frontal turret armor on production models with the Henschel turret measured 180 mm thick with minimal sloping. The massive cast turret front could defeat any Allied tank gun in service through late 1944 at all practical combat ranges. Side hull armor of 80 mm provided protection adequate against most Allied anti-tank guns at medium range, though not against heavy weapons or close-range attacks. Rear armor of 80 mm on the hull presented vulnerability to flanking attacks, but remained thicker than most tanks' frontal armor. The main armament represented the most powerful tank gun deployed in significant numbers during World War II. The 88 mm KK-43L/71 used a barrel 71 times the caliber in length. This extended barrel provided the acceleration distance necessary for extremely high muzzle velocity. Standard armor-piercing rounds left the barrel at 1,030 meters per second. This velocity combined with the projectile's mass to provide penetration capability exceeding any other tank-mounted weapon in widespread service. At 1,000 meters range, the gun could penetrate 237 millimeters of vertical armor plate. At 2,000 meters, penetration remained at 194 millimeters. These figures meant the Tiger II could destroy any Allied tank frontally at ranges where return fire remained impossible. Sherman tanks mounting 75mm guns could not penetrate Tiger II frontal armor at any range. Even the 17-pounder gun on British Firefly Shermans required side or rear shots at close range for reliable kills. The power plant attempting to move this 70-ton monster was the Maybach HL230P30 engine, the same basic engine used in the Tiger I, the Panther medium tank, and several other German armoured vehicles. This 12-cylinder gasoline engine in 60° V configuration displaced 23.1 litres and produced 700 metric horsepower at 3,000 revolutions per minute. Normal operational output was 600 horsepower at 2,500 RPM to reduce wear and extend engine life. This power output provided a power-to-weight ratio of barely 10 horsepower per ton, compared to 15.6 horsepower per ton for the Panther and 13 horsepower per ton for the Sherman. The Tiger II was severely underpowered for its weight. German engineers had requested a more powerful engine, but none existed in production or development that could fit in the available engine bay. The Maybach HL234 engine producing 900 horsepower was proposed but never reached production before war's end. The Tiger II would fight with an engine originally designed for tanks weighing 45 to 50 tons, not 70 tons. The transmission attempting to handle this power-to-weight mismatch was an improved version of the Maybach Olvar system. 8 forward gears and 4 reverse gears provided excellent gear selection for various speeds and tactical situations. The transmission incorporated lessons learned from Tiger I final drive failures by strengthening internal components and improving lubrication systems. However, the fundamental problem remained. The transmission was designed for tanks weighing 55 to 60 tons maximum. The Tiger II at nearly 70 tons exceeded design parameters by 15 to 20%. This overload placed stress on every mechanical component that contributed to premature failures despite engineering improvements over the Tiger I. Maximum road speed of 41.5 km per hour represented adequate performance for a heavy tank, but poor performance for the weight and engine power. Cross-country speed of 15 to 20 km per hour under favourable conditions meant the Tiger II moved slower than infantry advance rates across rough terrain. This limited cross-country mobility restricted tactical flexibility and made rapid repositioning difficult. German technical specifications listed operational range as 170 kilometers on roads and 120 kilometers cross-country. These figures assumed optimal conditions, with properly maintained engines and transmissions, careful speed management, and minimal tactical maneuvering. Fuel capacity of 860 litres in multiple tanks provided approximately 27% more fuel than the Tiger I, while the vehicle weighed 23% more. Road fuel consumption was specified at 5 litres per kilometre under ideal conditions. Cross-country consumption reached 7.2 litres per kilometre. These figures immediately concerned German logistics planners familiar with fuel supply problems that had plagued Tiger I operations. The Tiger II would consume fuel even faster, while German fuel production was declining due to Allied bombing of synthetic fuel plants. The Tiger II entered combat in small numbers beginning in May 1944. Heavy Panzer Battalion 503 received the first production vehicles for combat evaluation on the Eastern Front. Initial reports praised the gun and armour, while expressing serious concerns about mechanical reliability and fuel consumption. Battalion commanders reported that Tigers IIs could dominate any battlefield engagement, but could not move to distant battlefields without consuming entire fuel allocations. The Normandy campaign, beginning June 6, 1944, saw Tiger IIs deployed with heavy SS Panzer battalions, including the 101st and 102nd. These elite formations were equipped with the newest German armour and crewed by experienced tankers. Yet their combat reports documented the same pattern that would repeat across all theatres: devastating firepower, impenetrable frontal armour, and crippling immobility from fuel shortages. Heavy SS Panzer Battalion 101 War Diary entries from July 1944 captured the frustration. July 10th entry reported excellent combat results, with 11 Sherman tanks destroyed, at range exceeding 2,000 metres without loss. However, battalion could not pursue because fuel supplies were exhausted after 6 hours of combat operations, including movement to battle positions. July 18th entry noted fuel allocation reduced by 30%, with strict conservation orders. Tiger IIs restricted to static defensive positions only, offensive operations impossible without fuel resupply that higher headquarters could not guarantee. July 27th entry reported 3 Tiger IIs abandoned during withdrawal from Cancellia, all mechanically functional but fuel tanks empty. No fuel available for a movement. Demolition charge placed but effectiveness uncertain due to Allied pressure forcing hasty evacuation. The pattern established in Normandy repeated across every front where Tiger IIs operated. Soviet summer offensive in June and July 1944 saw Tiger IIs deployed with Heavy Panzer Battalion 507 on the Eastern Front. German after-action reports documented Tiger IIs destroying 34 medium tanks and even IS-2 heavy tanks at extreme ranges. But Soviet force quickly learned that Tiger IIs could not maneuver extensively without fuel resupply. Red Army doctrine adapted to exploit this weakness. Soviet commanders ordered units to avoid direct frontal assaults on Tiger II positions. Instead, maneuver forces around Tiger II flanks, forcing German commanders to choose between remaining stationary and being bypassed, or repositioning and consuming irreplaceable fuel. When Tiger IIs moved to counter Soviet maneuver, they burned through fuel supplies rapidly. When they remained stationary, Soviet forces isolated them and continued advancing. American intelligence first became aware of the Tiger II through British sources in mid-June 1944. Initial reports from Normandy described a new German super-heavy tank significantly more powerful than the Tiger I. Intelligence summaries described vehicles weighing approximately 70 tons with frontal armour, possibly exceeding 150 mm, and guns capable of destroying Allied tanks at range beyond 3,000 metres. These reports seemed almost fantastic to American armour officers who had spent 2 years learning to respect the Tiger I. The idea that Germany had developed an even more powerful heavy tank while clearly losing the war suggested either German desperation or Allied intelligence exaggeration. The reality would prove to exceed even the most pessimistic intelligence estimates. The capture of Tiger No. 507 in late August 1944 provided unprecedented opportunity for detailed evaluation. Soviet force advancing through East Prussia overran Henschel testing grounds at Marienburg, where multiple Tiger IIs sat in various stages of testing and acceptance. Most were destroyed by retreating German forces or damaged by Soviet artillery. But Tiger 507 survived intact with only minor battle damage. How this specific tank reached American intelligence teams remains partially unclear from available documentation. Soviet and American intelligence cooperation in 1944 included sharing of captured equipment for technical evaluation. American liaison officers in Moscow had requested access to captured German heavy tanks for detailed testing that Soviet facilities could not perform as comprehensively as American proving grounds. Tiger 507 apparently was diverted through these channels, though the exact administrative procedures are not fully documented in accessible archives. What is documented is that by early September 1944, American technical intelligence teams in Europe had access to an intact Tiger II for comprehensive testing. The question was where to perform detailed evaluation. Aberdeen Proving Ground in Maryland remained the premier American facility for captured equipment testing. However, shipping a 70-ton tank across the Atlantic required significant time and resources. Intelligence officers decided to perform initial mobility and fuel consumption testing in Europe, using captured German testing facilities and comparing results with German technical documentation. The testing team included Lieutenant Colonel Simon Tucker from Army Ordnance, Captain Frederick Morse, an automotive engineer drafted into intelligence work, 3 enlisted mechanics experienced with German vehicles, and 2 German civilian engineers who had worked at Henschel and agreed to cooperate with American intelligence in exchange for favorable treatment as the war ended. Initial inspection at the captured testing facility revealed that Tiger 507 was a mid-production model built approximately in May 1944. The tank mounted the production Henschel turret rather than the earlier Porsche turret used on initial production vehicles. This was considered the definitive Tiger II configuration and ideal for representative testing. German technical documents captured at the facility included detailed specifications, maintenance schedules, and most critically, fuel consumption data from Henschel acceptance testing. These documents would prove invaluable for comparison with American testing results. The documents revealed internal German concerns about Tiger II fuel consumption that had been expressed during development but overruled by military procurement offices demanding maximum combat capability regardless of logistical constraint. The American testing program focused primarily on mobility, characteristics, and fuel consumption because these factors would determine Tiger II operational effectiveness regardless of combat superiority. Testing began September 7, 1944 and continued through September 22 with multiple test runs under varying conditions. Initial road testing on paved surfaces confirmed German specifications. With full 860-litre fuel load, Tiger 507 completed 168 kilometers of road movement at steady cruising speeds before fuel exhaustion. This closely matched German claims of 170 kilometers road range. Fuel consumption averaged 5.1 litres per kilometre, again matching German specifications almost exactly. However, these results required optimal conditions. Smooth paved roads, steady speeds between 20 and 30 kilometers per hour, minimal acceleration or deceleration, no tactical maneuvering. These conditions bore no resemblance to actual combat, to operations. The American team proceeded to more realistic testing conditions. Cross-country testing over rough terrain revealed dramatically different consumption patterns. Test course included hills, soft ground, obstacles requiring speed changes, and simulated tactical conditions. Over measured 60-kilometer course, Tiger 507 consumed 730 litres of fuel, leaving only 130 litres remaining from the original 860-litre load. This represented consumption of 12.17 litres per kilometre. At this rate, operational range fell to approximately 70 kilometres or 43 miles under realistic cross-country conditions. But combat operations involved far more intensive demands than simple cross-country movement. Combat simulation testing produced results that shocked even experienced intelligence officers expecting poor performance. American test crews performed realistic combat tasks, including rapid acceleration, from stationary positions, emergency stops and direction changes, extended periods at combat idle, with engines running for observation, intensive radio operations requiring electrical power, turret traverse operations, simulated engagement sequences requiring gun elevation changes and ranging calculations. Under these intensive combat simulation conditions, fuel consumption reached an astounding 17.3 litres per kilometre. At this rate, the Tiger II's operational range collapsed to barely 50 kilometres, 31 miles. Captain Morse's initial report, dated September 15, 1944, expressed the results in terms that American logistics officers would immediately understand. The German Tiger II heavy tank consumes approximately 2.0 gallons of fuel per mile, travelled under combat conditions. This compares to approximately 0.6 gallon per mile for American M4 Sherman medium tanks under similar conditions. The implications were staggering. A Tiger II travelling the same distance as a Sherman consumed more than 3 times as much fuel. A battalion of 45 Sherman tanks required approximately 120,000 gallons of fuel weekly under active combat operations. A battalion of just 20 Tiger IIs required approximately 140,000 gallons weekly, despite having less than half as many tanks. When support vehicles, reconnaissance units, half-tracks, trucks, and all other battalion equipment were included, Sherman battalions required approximately 180,000 gallon weekly total. Tiger II battalions required approximately 220,000 gallons weekly total, more fuel for less than half the combat vehicles. And this assumed the Tiger IIs could actually operate continuously, which their mechanical reliability made unlikely. Colonel Tucker's summary assessment, compiled from all testing data, reached stark conclusions. The Tiger II represents the summary TASER's ultimate expression of German heavy tank philosophy, emphasizing maximum individual combat capability. Armor protection renders the vehicle effectively invulnerable to frontal attack by any Allied tank weapon in service. Main gun armament provides engagement capability beyond 3,000 meters with one-shot kill probability against all Allied armor. However, fuel consumption of 2 gallons per mile under combat conditions creates insurmountable logistics problems. Operational range of 60 miles maximum under combat conditions makes sustained mobile operations impossible. The Tiger II can dominate individual battles, but cannot prosecute campaigns requiring sustained movement across distance. German logistics cannot support Tiger II operations at tactically significant scale against enemies who control the air and systematically attack supply infrastructure. Every Tiger II deployed represents fuel resources that could sustain 3 Panther medium tanks or 6 Panzer IV tanks. The Tiger II represents catastrophic waste of scarce German resources in weapon system that cannot be adequately supported in field operations. The testing data was compiled into classified intelligence reports distributed through Army intelligence channels by early October 1944. All American armored commands in Europe received detailed summaries emphasizing that while Tiger IIs posed severe tactical threats, their limited operational range created exploitable vulnerabilities. Tank destroyer units received specific guidance about Tiger II engagement ranges and armor vulnerabilities. Infantry units were instructed that Tiger IIs moved slowly and could not pursue aggressively due to fuel constraints. Artillery forward observer learned that immobilized Tiger IIs made excellent targets for concentrated fires. Air support squadrons received target recognition briefings with emphasis on attacking fuel supply columns supporting heavy Panzer units rather than attempting direct attack on heavily armored tanks. American tactical doctrine evolved to exploit Tiger II weaknesses systematically. American tactical doctrine evolved to exploit Tiger II weaknesses systematically. Field manuals distributed in November 1944 emphasized maneuver warfare that forced German heavy tanks to reposition constantly. Each mile a Tiger II traveled consumed 2 gallons of irreplaceable fuel. Forcing Tiger IIs to chase American formations across extended distances, exhausted German fuel supplies faster than combat could destroy the tanks themselves. The Ardennes offensive in December 1944 would validate American intelligence analysis catastrophically for German forces. Operation Wacht am Rhein, Hitler's last major offensive in the West, committed virtually every available Tiger II to the attack. Heavy Panzer battalions 501, 506, and elements of several SS Heavy Panzer battalions deployed. Approximately 150 Tiger IIs and Tiger Is combined for the offensive. German operational planning assumed capturing American fuel dumps to sustain the advance beyond initial objectives. Each Panzer division received fuel calculated for approximately 150 to 200 kilometers of movement. Heavy panzer battalions equipped with Tiger IIs received proportionally more fuel, but still insufficient for sustained operations. If captured, fuel dumps could not be secured. Kampfgruppe Paper, spearhead of 6th SS Panzer Army, included Tiger IIs from 1st SS Panzer Division Leibstandarte Adolf Hitler. The battle group advanced approximately 60 kilometers in the first 48 hours, reaching its deepest penetration near Stoumont. Then, fuel exhaustion stopped all forward movement. Tiger IIs sat immobilized on Belgian roads with empty fuel tanks, while American forces regrouped and counterattacked. Major Hal McCown, an American battalion commander captured by Kampfgruppe Piper on December 19th, later testified about conversations with German officers during his captivity. SS officers openly discussed the fuel crisis. They desperately needed to capture American fuel dumps at Spa and Stavelot. When American forces held or destroyed those dumps, the entire offensive collapsed. McCown witnessed German tank crews siphoning fuel from disabled vehicles, trying to consolidate enough fuel to move at least some Tiger IIs. The effort proved futile. By December 22nd, Kampfgruppe Paper was surrounded with no fuel and no prospect of resupply. The unit abandoned all heavy equipment, including multiple Tiger IIs, and escaped on foot through American lines. Across the entire Ardennes battlefield, similar scenes repeated. Tiger IIs abandoned along roads and in villages, not from battle damage, but from empty fuel tanks. American forces advancing to recapture lost territory found dozens of German heavy tanks simply left in place when fuel ran out. Many showed no combat damage whatsoever. Crews had attempted demolitions but often lacked even the fuel necessary to move vehicles into good demolition positions. The American 9th Armored Division, advancing through St. Vith in January 1945, counted 17, abandoned Tiger IIs and Tigers Is within a 10-kilometer area. Intelligence teams examining the vehicles found 14 had been abandoned due to fuel exhaustion rather than mechanical failure or battle damage. German crews had literally run out of fuel in the middle of retreat and walked away from operational tanks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Post-war analysis of the Ardennes offensive by American and German historians confirmed that fuel shortages, not ammunition shortages or troop exhaustion or Allied air power, caused the offensive's ultimate failure. German forces actually possessed adequate ammunition throughout most of the battle. Infantry formations maintained reasonable cohesion through late December, but immobilized armor could not exploit tactical successes or protect infantry advances. German panzer divisions designed for mobile warfare sat frozen in place waiting for fuel trucks that never arrived. The trucks either did not exist, had been destroyed by Allied aircraft, or could not navigate congested roads clogged with abandoned vehicles and battle debris. The entire German operational concept collapsed when fuel supply failed. Tiger IIs, the most powerful tanks in the offensive, became expensive roadblocks rather than exploitation forces. The fuel consumption crisis extended beyond Tiger IIs to encompass Germany's entire approach to armoured vehicle design from 1942 through war's end. The Panther medium tank consumed fuel at rates that strained German logistics. The Tiger I consumed even more. The Tiger II represented the ultimate expression of this philosophy, consuming fuel at rates that made sustained operations impossible, even when fuel theoretically existed in rear area depots. German synthetic fuel production peaked at approximately 6 million tons annually in 1944, before Allied bombing systematically destroyed production facilities. This represented barely 1/10 of American petroleum production and had to support the entire German military and economy. The Luftwaffe consumed enormous quantities. The Kriegsmarine required fuel for submarines and surface vessels. The Wehrmacht needed fuel for hundreds of thousands of trucks, half-tracks, and other vehicles. Within this constrained supply, heavy tanks competed with every other consumer for scarce fuel. Each Tiger II operating for 1 week consumed fuel that could have operated 7 Panzer IV medium tanks. Each Tiger II battalion absorbed fuel resources equivalent to 3 medium tank battalions. A choice to concentrate resources in fewer, more powerful weapons, rather than distributing resources across more numerous adequate weapons. This choice made sense only if individual weapon superiority could compensate for numerical disadvantage against enemies capable of absorbing losses and replacing destroyed equipment rapidly, while systematically destroying German supply infrastructure. The choice proved catastrophic. American Sherman production totaled approximately 49,000 tanks by war's end. Germany produced approximately 1,490 Tiger IIs, 6,000 Panthers, and 8,500 Panzer IVs as primary battle tanks from 1943 through 1945. The numerical disparity was overwhelming, but operational availability rates compounded the disadvantage. Sherman operational availability averaged 70 to 80% throughout the war. Tanks damaged in combat received replacement engines, transmissions, or major components from well-stocked supply depots and returned to service within days or weeks. American armored divisions consistently fielded 90% or more of their authorized tank strength in actual combat operations. German heavy panzer battalions equipped with Tiger IIs averaged 40 to 50% operational availability at best. Mechanical breakdowns, fuel shortages, and spare parts unavailability kept more Tiger IIs under maintenance or awaiting repair than in actual combat. German armoured formations rarely fielded more than 60% of authorized strength and frequently operated at 40% or less. The multiplicative effect of these factors created battlefield superiority that German tactical skill could not overcome. American forces could afford to lose 3 Sherman tanks for every Tiger II destroyed and still maintain numerical superiority because replacement Shermans arrived within weeks, while destroyed Tiger IIs were never replaced. American tanks could maneuver freely across extended distances because fuel supply was adequate and reliable. German heavy tanks husbanded fuel carefully and avoided unnecessary movement because resupply was uncertain. American doctrine could emphasize aggressive mobile operations, exploiting breakthrough opportunities because logistics could sustain rapid advances. German doctrine was forced into defensive postures conserving scarce resources because logistics could not support sustained offensive operations. The war was decided not on specifications charts showing armor thickness and gun penetration, but in fuel trucks, supply depots, and maintenance facilities. The philosophical difference between American and German approaches to military technology shaped the war's outcome across every domain. German small arms were magnificently engineered masterpieces requiring skilled craftsmen and expensive production processes. American small arms were designed for mass production by semi-skilled workers in factories optimized for efficiency. Both approaches produced functional weapons. Only one approach produced weapons in quantities adequate to win. German aircraft emphasized sophisticated designs pushing performance boundaries with turbojets, rocket fighters, and advanced aerodynamics. American aircraft emphasized reliability, maintainability, and production efficiency, with designs that could be built by the thousands and maintained under field conditions. Both approaches produced effective aircraft. Only one approach produced air superiority. German naval design created submarines with revolutionary capabilities, including snorkel systems, high-speed underwater propulsion, and advanced torpedo technology. American naval construction focused on standardized designs that could be mass-produced rapidly with simplified systems that minimally trained crews could operate. Both approaches created capable vessels. Only one approach created the overwhelming numbers necessary for victory. The pattern repeated across every category of military equipment. German engineering excellence created weapons optimized for individual performance without adequate consideration of production feasibility, logistics sustainability, or operational maintainability. American pragmatic engineering created weapons optimized for mass production, reliable supply chains, and field maintenance by minimally trained personnel. Neither approach was inherently superior in abstract terms, but industrial warfare rewarded American pragmatism over German perfectionism. The Tiger II exemplified this German design philosophy perfectly. It was unquestionably the most powerful tank to see significant combat in World War II. Its armor protection rendered it effectively invulnerable to frontal attack. Its main gun could destroy any Allied tank at range exceeding 3 kilometers. In individual combat, the Tiger II was supreme. But war is not fought through individual combats in isolation. War is fought through campaigns spanning months and years across distances of hundreds or thousands of kilometers. War requires logistics systems capable of delivering fuel, ammunition, spare parts, and replacement equipment to forward units under enemy attack. War demands weapons that can be produced in adequate quantities, maintained under field conditions, and operated by soldiers with realistic training levels. The Tiger II failed every one of these requirements despite excelling at individual combat. German forces discovered too late that they had built an army around weapons they could not adequately support logistically. Tiger IIs required more fuel than supply systems could deliver. Panthers required more spare parts than production could manufacture. Tigers required more maintenance than field units could provide. Jet fighters required more specialized facilities than could survive Allied bombing. V-2 rockets consumed enormous resources for negligible military effect. Across every category, German technology had exceeded German capacity to employ it effectively. The result was a military force that appeared formidable on paper and performed impressively in individual engagements, but could not sustain operations at the scale and duration necessary for victory. The Tiger II, burning 2 gallons of fuel per mile while American bombers destroyed German refineries, symbolized the entirety of Germany's strategic failure. Post-war interrogations of German tank designers and military leaders revealed the internal debates that had occurred during Tiger II development. Engineers had warned repeatedly that fuel consumption would create insurmountable logistics problems. Procurement officers had acknowledged the concerns, but insisted that combat superiority would enable quick, decisive victories before logistics became critical. Hitler had personally intervened multiple times, demanding maximum armor and firepower, regardless of other considerations. The result was a weapon system optimized for short-duration breakthrough operations against enemies who would collapse quickly under concentrated attack. But by 1944, Germany faced enemies who would not collapse. The Soviet Union had absorbed catastrophic loss and continued fighting with seemingly inexhaustible reserves. The United States and Britain controlled overwhelming industrial capacity and could replace losses indefinitely. Germany's opponents would not accommodate German assumptions about short, decisive campaigns. The Tiger II proved devastating in defense during the war's final year. Heavy panzer battalions equipped with Tiger IIs consistently achieved kill ratios exceeding 10-1 against Allied armor. Individual Tiger II crews destroyed dozens of Allied tanks in single engagements. The Schwere Panzer Abteilung 503 claimed over 500 Allied tank kills on the Eastern Front. But kill ratios meant nothing when Germany could not replace losses while enemies could. A Tiger II that destroyed 10 Sherman tanks and was then destroyed itself, or abandoned for fuel shortage, represented a catastrophic German loss. Germany had no replacement Tiger II. America had replacement Shermans available within weeks. The mathematics of attrition warfare favored the side that could sustain operations indefinitely, not the side that achieved impressive individual combat results. Modern military education uses the Tiger II extensively as a case study in balancing combat capability with operational sustainability. Engineering students learn about the dangers of requirements creep and design overload. Military officers study the relationship between tactical excellence and strategic effectiveness. Logistics professionals examine the catastrophic consequences of inadequate fuel supply planning. The Tiger II teaches more through its failures than many successful weapons teach through their victories. Tiger number 5. 07. The tank tested by American intelligence in September 1944 survived the war and was eventually shipped to the United States for continued evaluation. It arrived at Aberdeen Proving Ground in Maryland in early 1946, where it underwent additional testing through 1947. The tank was eventually placed in storage and later transferred to the United States Army Ordnance Museum collection. Today, it remains part of the United States Army's historical collection, serving as a teaching exhibit for armor officers and military historians. The tank that once terrorized Allied forces now teaches American officers about the essential relationship between combat capability and logistics sustainability. Its 88mm gun remains silent forever, but the lessons it provides continue shaping American military thinking about weapon system development and procurement priorities. The capture and testing of Tiger 507 provided intelligence that fundamentally shaped Allied tank tactics during the war's final months. Understanding that Tiger IIs possessed crippling fuel consumption allowed Allied commanders to develop effective counter-tactics, exploiting this weakness without requiring equivalent firepower or armor protection. Maneuver warfare forcing Tiger IIs to reposition constantly exhausted German fuel supplies. Air interdiction targeting fuel supply infrastructure immobilized German heavy armor more effectively than direct tank combat. These tactics, informed directly by intelligence gathered from captured Tiger 507, saved Allied lives and accelerated German defeat. The 70-ton steel monster that seemed invincible in direct combat proved vulnerable to systematic exploitation of its logistical weaknesses. Superior weapons could not compensate for inadequate logistics. Individual excellence could not overcome systemic sustainability failures. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The Tiger II stands today as monument to German engineering ambition that exceeded strategic reality. It was simultaneously the most powerful tank of World War II and one of the most strategically counterproductive. It represented technical excellence divorced from operational feasibility. It embodied a design philosophy that lost Germany the war, despite winning individual battles. The most dangerous tank ever built, ultimately defeated not by superior enemy weapons, but by its own insatiable appetite for fuel that German logistics could never adequately satisfy. In that paradox lies the complete story of the Tiger II and the ultimate lesson about modern mechanized warfare. Sustainability defeats superiority when wars extend beyond single battles into campaigns spanning continents and years.